Okay, what we're going to start with today here is there's ultimately kind of three parts to our first lesson here for section 6.1. And the first one is going to be doing similar work to what we've already been doing here in terms of evaluating integrals. Most of the integrals that we've dealt with so far have been definite integrals, which means that we've used the fundamental theorem, we found an antiderivative, we plugged in the upper and lower limits and did the subtraction, and we got a final answer, some numerical answer which ultimately represents the area under some curve, and depending on the context, it could represent a number of trees in a forest. It could represent a number of a volume of water in a pipe, blah blah blah, whatever the case may be. We've seen some different applications for that, and we're going to continue to do that same thing. And like I said, today the first part here we're going to look at it in very similar context. And the first part though is if I have an integral that was something like, let's say, secant squared x dx, and I want to know what does that equal. Okay. So ultimately the question then is the difference between this integral and the ones that we've done so far is what do I notice that I don't have here? There's no limits. Okay. So what does that mean then if I have an integral that has no limits on it? And ultimately what it means is that this is what we call an indefinite integral. A definite integral is going to give us the area under some curve. Okay? An indefinite integral, we're going to do exactly the same thing using the fundamental theorem, but we don't have any numbers to plug into it, so we're not going to be able to come up with a numerical answer. So ultimately what this is indicating is that we just need the antiderivative. Okay? So the antiderivative here, of course, is tangent. Secant squared's antiderivative would be tangent, because if we differentiate tangent, we get secant squared. And ultimately, though, keep in mind, though, that if this indicates that I want the antiderivative of this, okay, is tangent the only possible answer here? It's got to be tangent x plus c. Because ultimately, this would give us a family of functions. It could be any c possible here. Okay, could be shifted up or down any amount of units. All right. So ultimately, our work in terms of evaluating is not much different than what we did for definite integrals. We're just going to find the antiderivative and add a plus c on the end, and that's it. So we won't plug in any numbers because there are no numbers to plug in, and that will do it. Okay. So ultimately, there's some vocab words on there on page 306 that we've already essentially studied. And then the other portion I wanted you to look at here is on page 307. We have a list of integral formulas, if you will. And again, you have this list, which you can see on your page 307. Can't see that far. But ultimately, it gives us a list of indefinite integrals, which we can in turn use for definite integrals as well. So you'll notice that the very first one is if we have some power function x to the n, okay, and it formalizes what we already have known about the power rule, if you will, for antiderivatives, and that's the fact that we're going to add 1 to the power and we're going to divide by the new power. So again, it's just a formal version of what we've already been doing in terms of finding antiderivatives of power functions. And then one of the questions here is, notice this is 1 part b, because ultimately the 1 over x function is x to the negative 1, which is a power function. Think about why the power rule in part A doesn't work for that. If I had x to the negative 1, I would add a power, I'd get x to the 0, which is fine, but it would be divided by what? And we're adding 1 to the power, and we're dividing by the new power. So it'd be x to the 0 over 0, which is what? Undefined. Okay? And ultimately, we know that the antiderivative of 1 over x is ln x. And keep in mind that it's the absolute value of x. That's an important part here. That it needs to be the natural log of the absolute value of x here. Okay? So with that said, we know how to handle essentially any power function then at this point, whether it be x to the anything positive, anything that's a fraction, anything that's negative. If it's x to the 0, of course, it's just a constant. And then x to the negative 1, we can account for that not working with the power rule by the fact that x to the negative 1 is actually just natural log of absolute value of x. All right, and then there's some other formulas here for common functions that we use, like e to the kx. So if anything that's of the form e to the kx is going to be itself divided by k, which ultimately is the inverse operation of what we did when we differentiated. Same thing with sine and cosine. Sine kx's derivative is going to be negative cosine kx divided by k, because if we differentiated cosine kx over k, we get back to sine kx. Okay. Same thing with the cosine k. Secant squared, we just did that a minute ago. Cosecant, we know that those all just comes right straight from our derivative formulas that we already had memorized. And like I said, they all stem from the related derivative formulas. Okay? So we're just going backwards with the rules that we have already developed for our other functions. So again, these are some common integral formulas. There could be other integral formulas. In fact, if you look at the back of the book, there's a fairly monstrous table of integral formulas that we essentially won't use in this class. Okay? But if you continue on in further calculus classes, you will eventually use those tables more thoroughly. But bottom line is, these are, like I said, the most basic functions that we generally use. Of course, all the integrals that we solve and are going to solve aren't going to be as easy as just looking at the formula and getting the answer. There's going to be some more work involved, which we'll get to in a little bit. All right, so if you take a look here, just as a couple examples. If you look at number 4, part B here on page 308, they give us 1 over radical x dx as our indefinite integral. And so with that said, we would write that as a power function. Would be step 1. And then step 2, the antiderivative of that would be x to the positive 1/2 divided by 1/2. We use our power rule, so straight power function. And if we instead of divided by 1/2, we multiply by 2, we'd ultimately get 2x to the 1/2, or 2 radical x, plus what? Plus c. So that right there would be our antiderivative for 1 over radical x. Okay. And again, if we're doing an antiderivative here, if this was on a quiz or test, is there any way that could be checked? Couldn't you just differentiate this and make sure it gets back to the integrand? All right. Another one, if you look at part D, we have cosine of x over 2 as our argument this time, our integrand. I would first write that as cosine of 1/2 x if I were you, just to make sure I can keep straight what my actual k is here. And again, this is our of the form cosine kx. So again, what would we get if we anti-differentiated? Okay. Ultimately, the antiderivative here would be sine of kx. So sine of 1/2 x. And remember, when we're doing derivative, we multiply by the inside function's derivative, if you will. But this time we'll divide. And so we'd ultimately get 2 sine of 1/2 x plus c. And that would be our antiderivative. And again, to illustrate why is it divided by in this case when we go backwards? Because if we were to differentiate this, we'd get, the 2 would already be out there. We'd have cosine of 1/2 x. True? That would be our derivative. And then the derivative of the inside here is 1/2. And what would the 1/2 and the 2 do? They cancel each other out and we get back to the integrand, which is cosine of 1/2 x. Okay. So ultimately we're reversing the chain rule by doing that particular step. Okay. All right. On the bottom of page 308, we also have our properties of indefinite integrals. And these are, of course, the same properties that we had for definite integrals. And we're allowed to factor out any constant multiples. Okay, so if there's a constant multiple on your integrand, take it out. Okay. If your integral is negative, or your integrand, I should say, is negative, you can take it out, the negative sign. The negative is just multiplied by -1, so take that out just like you did in rule number 1. And then the sum and difference, we can differentiate, anti-differentiate part by part, just like we did with our definite integrals. So they give an example on page 309 here of x squared minus 2x plus 5. And ultimately, if we just go term by term, we can get x cubed over 3 minus x squared plus 5x plus what? Plus c. And that would be the indefinite integral of that function, okay, which ultimately, again, is just the antiderivative of said function. Okay. All right, so that's going to be our part 1.